When we talked about CSTRs, we showed that two CSTRs of equal volume in series could yield a higher conversion than a single CSTR that was twice the size. And given our discussion in the last lecture about PFRs, that begs the natural question, would this also work for a PFR? And to answer that, we'll start at the result of the mole balance for a PFR, right? DFA dV is equal to RA. And if we consider the simple reaction just A goes to B, with the rate constant K1, of course, RA just equals minus K1 times CA. And so, DFA dV equals minus K1 times CA. And we've made this substitution now a couple of times where we know that CA times the volumetric flow rate is equal to FA. So this becomes dCAV dV equals minus K1 times CA. And of course, if the volumetric flow rate is equal to a constant, it can come out of that differential. And we get the volumetric flow rate times dCA dV equals minus K1 times CA. And then dCA over CA equals minus K1 over V dV. Okay. And of course, if we have two PFRs in series, this mole balance is going to hold for both of those reactors. And so one of the things that we could do is take this expression and integrate it for reactor 1 and also do the same thing for reactor 2. So the first reactor, you have whatever the initial concentration is entering the first PFR. So if we have two PFRs in series, right, it would look, something like this, right? And we would have, the concentration of A entering. We would have what I'll call CA1, which is the interim concentration. And then we would have, of course, the exhaust concentration, right? Where that's reactor 1 and that's reactor 2. So for the first reactor, if we did this integration, will be the integral from CA0 to CA1 of dCA over CA equals the integral, or I guess these are constants. We could leave that as minus K1 over V times the integral from 0 to V1 dV. And the result of this integral, of course, is just the natural log of CA1 over CA0 equals minus K1 over the volumetric flow rate times V1. Okay, so we're gonna just put a little star next to this and say, that's the result coming out of reactor 1. Well, let's do the exact same thing for reactor 2. And here, of course, the inlet concentration into reactor 2 is just CA1. So this is the integral then from CA1 to CA2 of dCA over CA equals minus K1 over V. And now when we're looking at this problem, right, so we have some volume here of this reactor, which is the integral, and let's say that they're the same volume. So we are going to go from 0 again to V1 of dV, okay? And if we look at this, well then our solution is that the natural log of CA2 over CA1 equals minus K1 over V times, again, V1, right? So this is coming out of reactor 2. And to see what would happen, we're just going to add these two equations to one another. And we'll get the natural log of CA2 over CA1 plus the natural log of CA1 over CA0 equals minus K1 over V times V1 minus K1 over V times V1. And so this sum then becomes the natural log of CA2 over CA1 times CA1 over CA0 equals 2 times V1 times minus K1 over the volumetric flow rate. And of course, those two cancel. And we end up getting this expression that the natural log of CA2 over CA0 equals minus K1 over the volumetric flow rate times 2V1. Now, what does this actually mean? Well, if you look at this, this would be identical to if we had just integrated from CA0 to CA2 of dCA over CA, and that would have been equal to the integral from 0 to 2V1 of minus K1 over the volumetric flow rate dV. So unlike a CSTR, in a plug flow reactor, it doesn't actually help us to break things up into multiple reactors in series most of the time. You certainly wouldn't do it to boost conversion. You could have a bunch of parallel tubes that would allow you to increase capacity of your plant. You also, depending on the process, might put some plug flow reactors in series to help with maintenance, but you certainly wouldn't do it to increase conversion. So the much, much more common thing is to have PFRs in series with other reactors. And the most common configuration really is to have a continuously stirred tank reactor at the beginning, and then to have a plug flow reactor almost as a polishing reactor. Because if you remember when we talked in the last lecture, if we looked at, 1 over the inverse of the rate versus our conversion, that if we were to have what would look like sort of a regular plot here on this Levenspiel plot, you could have one huge reactor, right, if you were going to come all the way out to here. Or one of the things that you can do instead is you could have a CSTR that gets you most of the way there, and then you could have a plug flow reactor that then fills in this gap. So it is extremely common to have a CSTR and then to have a PFR. Okay, and then the overall volume of the system is less, which means the reactors probably cost less, etc. So what I would like to do is to solve a problem where we look at a CSTR as an initial reactor to increase the conversion, and then we have a plug flow reactor that takes it to the final conversion that we're interested in. And here's the problem statement for that. And we're going to consider an ideal CSTR and ideal PFR in series. We have a mixture of A and B being fed to the CSTR at a volumetric flow rate of 120 milliliters a minute. The solution is 1.2 molar in A and 1.5 molar in B. And the following reaction is happening, right? A plus B goes to C plus D. The reactor cascade is designed such that the conversion leaving the CSTR is 0.3, and the final conversion leaving the PFR is 0.85. Determine the volume of the two reactors. And then finally, what would the length of the PFR be if the internal pipe diameter is 8 inches? Okay, so first, let's look at the CSTR. Okay, we have A plus B goes to C plus D, right? And we have K1. So we know that our rate law, if this is an elementary reaction, is that RA equals minus K1 times CA times CB. And if we utilize the result of the mole balance for CSTR, we know that FA0 minus FA plus RA times V is equal to 0. And of course, we've done this substitution before where we know that FA just equals FA0 times 1 minus X in this case. And so that if we make that substitution, then FA0 minus FA is FA0 minus FA0 times 1 minus X, which is just FA0 times X. So we're going to use that and make that substitution here. And so this becomes FA0 times X minus K1 times CA CB is times V is equal to 0. And if we're looking for the volume here, well, then we can just solve for the volume. And that's equal to FA0 times the conversion divided by K1 times CA times CB. Now with this relationship, we know that the concentrations of A and B are also a function of the conversion. And we've derived expressions for this over the course of the last couple of lectures. And in this case, there's no change in the number of moles, or it could be a liquid phase reaction because we're given the concentration of the solution. So solution is a really nice sort of code word for this is a liquid. And when that's the case, we know the volumetric flow rate in and out of the reactor is going to be the same. And so then the concentration of A can be simplified. This is just Ca0 times 1 minus X. And of course, CB0, we could write two different ways. We could write it as CB0 minus Ca0 times X, right? That's one way to write it. There's the alternative form that CB0 equals Ca0 times theta B minus X, right? Where that theta B is equal to the initial concentration of B over the initial concentration of A. And both of those are okay. And I use them, almost interchangeably. And so then our result for the mole balance here, just putting these expressions for Ca and Cb into our equation for volume, we have that the volume equals Ca0 times the volumetric flow rate times the conversion divided by Ca0 times 1 minus X times Cb0 minus Ca0x times K1, right? That's sort of the black form of this equation. If we wanted to use theta, we could write an equivalent expression and find that the volume of our CSTR would be equal to Ca0 times the volumetric flow rate times X divided by Ca0 squared times 1 minus X times theta B minus X times K1. And some like the magenta form of this equation because it simplifies even a little bit more, that this squared gets rid of that Ca0 and you're left with the volume is the volumetric flow rate times the conversion over Ca0 times 1 minus X times theta B minus X. I personally don't have a preference for which form you choose to use. Now, we know these from the problem statement directly. So I'm going to use the magenta form of this equation. So I know that theta B is equal to the ratio of the concentrations, or the initial concentrations. So that was 1.5 molar for B over 1.2 molar in A. And so that's equal to 1.25. So if I go about solving this, I get that the volume of our CSTR is then equal to our volumetric flow rate, which was of course 0.12 liters per minute from the problem, the conversion, which was 0.3 leaving the reactor, times the inlet concentration, which is 1.2 moles per liter, times 1 minus 0.3 times 1.25 minus 0.3, then times our rate constant, which was 0.0036 liters per minute times moles. And one of the things I like to do when I solve all of these problems are to make sure that the units cancel. So I know liters there cancels with liters there, minutes here cancels with minutes here, and moles here cancels with moles there. So we have 1 over the liters, which is just liters. And so we can solve then for the volume of our CSTR, and that equals 12.5 liters. Okay, so that's the first part of this problem. Does anybody have any questions about this? All right, if that's the case, now let's move on to the PFR, okay? And there are two ways to look at the PFR. And we'll talk about each one of them. But one of the things to remember is that in the PFR, the concentration is no longer equal to Ca0 because you've already converted 30% of A and B into the products. So that's one of the things to remember. So we're going to say, so for our PFR, at volume equals to 0, Ca actually equals Ca0 times 1 minus x, which is 1.2, or x for the CSTR. And that's 1.2 times 1 minus 0.3, which is 0.84 molar. And Cb into the PFR equals our Cb0 minus Ca0 times x, which equals 1.5 minus 1.2 times 0.3, which is 1.14 molar, okay? And so what we're going to be looking for in this problem is when do we have an overall conversion of 0.85? And that is achieved, so our goal here is when we are at Ca0, the initial Ca0 times 1 minus 0.85. So our target here is to find where we're at 0.18 molar, okay? And so let's apply our PFR equation here. So we know that dFA dV equals RA again. And of course, that is dCAV dV minus K1 times Ca times Cb. And the volumetric flow rate here is a constant because we said we're in the liquid phase. So that means that dCA dV is equal to minus K1 over the volumetric flow rate times Ca times Cb, okay? So one way to solve this problem is to stop here and then to do the exact same thing for B. And we'd find that dCb dV also equals minus K1 over V times Ca times Cb, right? And from here, we could use Euler's method, right? We could implement these two equations in Excel, or you could use MATLAB, and to parametrically change the volume until you get to the conversion that we're looking for, which is 0.18 molar, okay? Now, if you were to do that, right, you would get a plot. And let's show you what that would look like, okay? So there is the conversion for this particular example, implementing Euler's method as a function of the PFR volume. And if our conversion goal is 0.85, you know, that means we're about here. You come over and go down, and you know, you can read this off the graph, right? And you can say that it's 75 liters, okay? But you don't have to use Euler's method here. So you can also do the integration and do this as a function of the conversion. And if we were to do that, we would start with the equation that we derived just a second ago, that dCA dV equals minus K1 over the volumetric flow rate times Ca times Cb. And of course, we've already written this before, that Ca is Ca0 times 1 minus x. That means that dCA is just equal to minus Ca0 dx. So the differential on the left-hand side becomes minus Ca0 dx dV equals K1 over V times Ca Cb. And there should be a minus there. And so those two negative signs, right, those cancel. So those become positive. And then we can insert our expressions for Ca and Cb. So this would be Ca0 times dx dV equals K1 over the volumetric flow rate times Ca0 times 1 minus x times Ca0 times theta B minus X. And we get this form that where, I'll do this first, where one of the CA zeros at least is going to cancel, and you're left with dx dv equals K1 CA0 over the volumetric flow rate times 1 minus X times theta B minus X. And if we were going to integrate this, of course, you'd have to get all of the conversion to the left-hand side of this equation. So this would be dx over 1 minus X times theta B minus X equals K1 CA0 over the volumetric flow rate dV. And in this case, right, this would be integrated from 0 to the volume. And that brings us to the limits of the integration here, right? This would be from the inlet conversion, which is the conversion that we got for the CSTR, right? That was equal to 0.3. Then to the final conversion, which is 0.85, okay? So this integral is not too bad. It is in the integral tables. So as you're solving problems, whether it's in the homework or on the exam or a quiz, you might want to have integral tables handy just in case you get an integral like this that you're not super comfortable with. This could be slightly easier. So in a lot of problems, we'll solve where theta B is equal to 1, where the two concentrations are the same. And then that integral becomes relatively simple, right? That would be the integral from x1 to x2 of, dx over 1 minus x squared, right? And that one is, that one is okay, right? That's just 1 over 1 minus x. So, that one's not too bad, and it's something that's very, very common that we've done before. So I'll let you guys, for this slightly more complicated one, go over this in your preparation and studying. And if you do this, you'll get the exact same answer, that the volume is equal to 75 liters. So both the direct integration and the Euler's method led us to exactly the same place, that the volume was equal to 75 liters. Now, the last part of this example problem asked us to find the length of the PFR if the internal pipe diameter is 8 inches. So we discussed in the last lecture how you can convert several variables, right? That you have the volume, tau, length, those are all fairly equivalent to each other. And so, in our problem here, well, we know that the volume of our cylinder, right, of our plug flow reactor is just the area times the length. And of course, the area is just pi times the radius squared. And we know that from the problem statement that our diameter is 8 inches, right? So that means the radius is equal to 4 inches. And if we want to get that in terms of feet, right, it's 4 over 12 feet, or 2 over 6. So that means that our area is equal to pi times 4 inches divided by 12 inches per foot squared. And that gives us an area of 0.35 cubic feet. And we know from our problem statement that the volume, or from our solution, I'm sorry, is 75 liters. Well, of course, that just equals 0.075 cubic meters. And then we can do a simple unit conversion. So we know there's 3.28 feet per meter, right? And we're going to cube that. And then we get our volume is equal to 2.65 cubic feet. So our length then is just the volume over the area, which is 2.65 cubic feet divided by 0.35 square feet. And sorry, I wrote cubed before. There we go, that's fixed. And so then the length that we calculate is 7.58 feet, would be the length of the reactor for us to achieve that conversion. And if we want to double check with our Euler solution, we could do that. And we could use that exact same unit conversion I did a second ago to convert from volume to length. And again, we were at right about here, right? And we can come over and come down. And, you know, that's 7.5, 8, something like that. So we also could have read it off the plot, okay? Okay. So in that problem, what we tried to do was to show how two reactors can work in series. One of the things that I really want to stress is when you're thinking about the second reactor, don't forget that you're not at the initial concentration, right? You're at the concentration that's coming out of the first reactor as you enter the second one. And as you go through the problems for the homework and studying and doing all that for quizzes, exams, etc., you know, please keep that in mind. And it's something that I guarantee at some point here we're going to see more problems where there are multiple reactors that are linked to one another, and that's something that's good to keep in mind. Does anybody have a question about this example? Okay. If not, let's do a new example. You might think, based on our discussion so far, that CSTRs are doomed to be these huge reactors that get relatively poor conversion compared to PFRs. But that doesn't necessarily have to be true. And so let's consider the exact same reactor, right? The exact same size that we had in the previous problem where we were 12.5 liters, except now we're going to figure out a way to boost the conversion or get the concentration of A and B as low as we can inside of our reactor. And one way to do that is a recycle stream. And if I draw that, you know, maybe how we would implement this. So we're used to drawing our CSTR kind of like this, right? Well, at least I like to think of stirred tanks as liquids, even though that's not always the case. And we think, all right, we have one stream that's leaving, and then we have one stream that's coming in. And the thing about a CSTR is that you're always operating at the most dilute point. And so getting to high conversions means getting this, you know, to the lowest concentration of A or B. In this particular case, you have both of them, right? So how would you do that? And it turns out one way to do that is to introduce a recycle stream. So let's say that we have a separations process that is happening here, and some flow is going to leave there, and some flow is going to get rerouted, right? So we're going to have a mixer here, and leaving the separator, we have a stream like this. And then, of course, now we have our initial inlet flow, okay? And one of the things that you might think is when you do this separation, that you want to take out C and D, and then you want to push forward A and B. And you would naturally think that because you think, okay, if I'm going to boost the conversion, I want the reaction to happen faster. And one way to do that is to increase the amount of A and B inside of the reactor. But it turns out that that doesn't work particularly well. In fact, if you do this separation and you add A and B into the mixer, though you boost the overall reaction rate and the amount of material that you make, you do not boost the conversion. In fact, you lower the conversion. It turns out that a much more effective way to do this is that we're going to separate out part of C and D only, and we're going to feed that back into the CSTR. And it's using the fact that the CSTR works based on dilution to our advantage. And leaving here will be the rest of A and B and some of the product. So we're going to recycle product to boost the conversion, which probably makes absolutely no sense. But you know, take a step back and think about it. I think that'll help. So how much C and D should we add? And how much would that boost the conversion? Well, that's a really good question. And to do that, we oftentimes control this ratio, the flow rate of that stream, which we'll call FR, and the flow rate of that stream exiting that we'll call FE. And so we define this thing usually called the recycle ratio, which is R, which is equal to this flow rate, FR over FE. And what that leads to then is a volumetric flow rate that is essentially, since these are both in the liquid phase in this problem, that our volumetric flow rate is also related to this, right? So we have some initial amount that's coming in, right, at some volumetric flow rate V0. We have some volumetric flow rate that's coming in here, which we're going to call, VR, which really is just V0 times the recycle ratio. And then the volumetric flow rate into this reactor is really then just V0 plus V0 times the recycle ratio. And of course, if everything's running at steady state and these are liquids, the volumetric flow rate here and the volumetric flow rate here have to be the same. So hopefully what we can do now is a mole balance on the CSTR and try to see how this gets implemented into boosting the conversion. Okay, so let's do this. So let's take this concept and apply our CSTR equation. So remember, for a CSTR, we're operating at steady state. So this is just in minus out plus generation minus consumption equals accumulation. And I wanted to start there because we now, if we draw our boundary around the CSTR, we have different considerations here. So what comes in and what is leaving? Well, the only thing that is actually entering, if we do this mole balance on A, is that this stream only contains C and D. So nothing's really coming in with regards to A from the recycle stream. So we really only have to worry about the part of this stream that comes from the initial flow rate in. And so when we do that, this just becomes, it's still CA0, right? Because we have some CA0 there, times the volumetric flow rate that's entering. And then leaving, now we have a volumetric flow rate that is this plus that, and we're at whatever the reactor concentration is. And we've just called that CA. So that's times V0 plus V0 times the recycle ratio, which we talked about just a minute ago. And then we have RA times V as our consumption, generation minus consumption. So this becomes just minus K1 times CA CB. Sorry, that C is a little wonky. Let me rewrite that. CA CB times V. And that's equal to 0. Okay. So what is this going to do to our balance? Well, the first thing that you can see is that we should insert our expressions for the concentration of A and the concentration of B. So this becomes CA0 times V0 minus CA0 times 1 minus X times V0 plus V0 times the recycle ratio minus K1 CA0 times 1 minus X times CB0 minus CA0 times X, right? And that's times the volume, and that's equal to 0. And we could divide through by CA0, and you'll get rid of this term, and that one. And what we're going to be left with here is that V0 minus 1 minus X times V0 plus V0R minus K1 times 1 minus X times CB0 minus CA0X times V is equal to 0. And we really only have a couple of other things to do here. One is that when we FOIL this out, right, this is just V0 minus V0x plus V0r plus V0r times x. And when we do that, that V0, right, this is subtracted, right, minus all that stuff. So that V0 is going to cancel with that one. And so once we have that, I'm just going to combine terms. I'm not going to go through like all the tiny little details, because you guys can also do that. And we're going to end up with this expression that we're going to FOIL all this out and have terms that are squared in x, that are also first order in x, and terms that don't have x at all. And so we're going to get a functional form that is x squared times minus k1 Ca0 times the volume plus x times V0 plus V0 times R plus K1 Ca0V plus K1 Ca0 Cb0 times V plus negative V0R minus K1V times Cb0. Okay. And that's equal to 0. And so we can solve this problem by parametrically changing the recycle ratio, right? We're really interested in how conversion changes with that. And once we do that, we'll just solve this equation using negative b plus or minus the square root of b squared minus 4ac over 2 times a, where of course this is a, this is b, and that's c. Okay, and I just want to show you guys the result, because even though we've been going through the math isn't really the point. The point is to get to here, where we can change the recycle ratio, and as we increase it, the conversion goes up. So our little 12.5 liter batch reactor, or sorry, CSTR, that was only able to achieve a conversion of 0.3 without recycle, now we introduce this diluting stream, and we can achieve much, much higher conversions. Now, that's not free. That does happen with a reduced overall reaction rate, but we can increase the conversion, which is good. It also adds infrastructure into our system, which can increase cost and complexity and all that kind of stuff, right? Because we had to add a separator, we had to add a mixer. There's definitely, if it's a liquid, there's going to be new pumps everywhere and new temperature controllers and all that stuff. So you do add some complexity, and offsetting the cost of all of that with how much you sell the product for, how important size is in your facility, as well as the initial capital cost for a smaller versus a bigger reactor. All those would come into play in the future.